Maybe I'll go through it a little bit. If I say something like a times b squared, that's just a squared b squared, yeah? Are you happy with that? What about a times b to the power 3? Well, that's just a cubed b cubed, yeah? What about a to the power b squared? That's just a to the power 2b. Because this one is just a to the power b times a to the power b. So we've got b copies of a here and another b copies. We've got 2b copies altogether, yeah? So e to the minus n squared is just e to the minus 2n. Yeah? And that's all I've used here. Also, to get from here, this is n to the power n squared. That's just n to the power 2n. There you go. That's all that is. And why is it 2 pi n, not square root of 2 pi n? It's because I'm squaring a square root to get back to where I started. I will put a powers sequence of screencasts up online if you want to catch up. But you've got to watch it and you've got to internalise it because it's necessary for all the course. All right, so we've got n factorial squared and 2n factorial. So what I'm going to do now is go back to my binomial distribution, which is here, 2n factorial over n factorial squared times a half to the power 2n. You happy with that? Do you know where that comes from? It's because it's p to the n, 1 minus p to the n as well. So it's a half to the power n times a half to the power n as well. So I've got 2n altogether. Yeah? Well, all I do is just write out what these guys are here. Not equal to. Approximately equal to, because I'm going to be using Stirling's approximation. Let's see what happens. Something quite magical happens here. I still get a kick out of this, even now. And I learned this 20 years ago. No, 30 years. Quite a long time ago. I still get a kick out of it. Let's just substitute in and see what happens. 2n factorial is root 2 pi times 2n e to the minus 2n times 2n to the power 2n from there over n factorial squared, which is this term here, 2 pi n e to the minus 2n n to the power 2n times 1/2 to the power 2n. All I've done is write out the n factorial squared. And now we can do some magic. Now I can do some cancelling. Straight away I can do some cancelling. Let's have a look. I'll use red to cancel. The e to the minus 2n goes, of course, straight away, for junk. For junk. This one here, I'm going to rewrite that just with my finger. I'm going to rewrite that as 2 to the 2n times n to the 2n. Because it was 2n all to the power 2n. Why am I doing that? Because I can do this. Haha. That's nice, isn't it? What else have I got? I'm going to rewrite this term here and this term here in a slightly different way. I've got a fraction with 2 pi n on the top, and I've got 2 root pi root n. Sorry, that's on the bottom, isn't it? That's the bottom, that's the denominator. It's just that. And this, why is that 2? It's because it's the square root of 4, which is 2. Root pi, which is that one there, and root n, which is that one there. And now I can get my magic pen out and do a bit more cancelling. I can cancel that with that. Yeah? Which equals 1 over root pi n. Why? Because I've got a square root of pi over a square root of pi all squared, and I've got a root n over root n all squared. So everything cancels out quite nicely. Quite a lot of work. However, we've got this beautiful system here. Let me remind you why I'm doing all of this. We've got 2n trials, each with p equals a half, probability of success, then the probability of having n successes and n fails, an even split, is approximately, I'll say I'm writing equals and it shouldn't be, approximately 1 over root pi n. It's worth observing, there's no circles in this. Pi, when you learn about it at school, pi is the ratio of a circle's circumference to its diameter. And you think, oh, well, so much for circles. Here, pi has cropped up through the back door, so to speak, into statistics. And we'll see that when I cover the Gaussian distribution a bit later on. So, let's have a look at this. If I say n equals, let's say, 20, the probability that r equals 10, number of successes equals 10, the way to think about it is a party with 20 children. You'll know I've got children, so lots of my examples are from domestic family life. So if I have 20 children at a party, what's the probability that there's 10 boys and 10 girls? It's nice if everybody pairs up, but, well, I can just write it out. It's 1 over the square root of pi times 10. One over the square root of 31.4, which is about 17%. Oh, sorry.
Isn't in 20? If it's pi in, shouldn't it be pi times 20?
No, because my number of trials was always 2n. So if there's 20 children, n is 10, and the total number of trials is 2n. I can verify this in a couple of ways, of course. Whenever I'm applying some clever dick, super duper complicated stuff here, there's lots of opportunity for error. So I'm going to have to verify it, and of course I'm going to verify it by checking against the exact answer, which in this case is not hard to calculate it. Oh, here it is. And look, it's correct to 2 decimal places, and it's only a very, very tiny error. Furthermore, you can see quite nicely that as a function of n, we've got this rather nice behavior that the probability of having an exact match between the boys and the girls decreases with increasing n, because the probability of a match, the probability of pairs, equals 1 over root pi n. So as n gets bigger, we're taking the square root of a bigger and bigger and bigger number, and it decreases, the probability decreases. And as we've demonstrated, well, not proved, but demonstrated, this is actually quite an accurate formula. It's more accurate than Stirling's approximation itself, because the different errors tend to cancel each other out in a pleasing way, but not absolutely. So let's go back to the context of hypothesis testing. And if I've got n equals, let's say, 100 children, and I've got r equals 50 boys equals success, and n minus r equals 50 girls, of course, equals fail. Somebody might suggest, you might say, they were invited in pairs. You might say that because you've got an exact balance between boys and girls. There's a nice statement about the world. The null hypothesis, sorry, the hypothesis is they were invited in pairs. That's why we've got a match, because they might be dancing or something. I've got to be careful with political correctness here, but it doesn't really matter if your kids are 5 years old. What's the null hypothesis? The null hypothesis is the negation of what you're looking for. So somebody says, I bet you invited them in pairs, so there's no boys left over and no girls left over. But the null hypothesis is pretty much that the genders were independent, were random, independent, with probability of having a boy being a half. So there's my null hypothesis. And of course, what I've got is some data. If I've got my data of 100 children with exact balance, I can work out what the probability of my null hypothesis, the probability of my data, the probability of my observation is if my null hypothesis is true. And we'll work out what our p-value is. You'll remember the definition of p-value. The p-value equals the probability, if the null is true, of obtaining the data set D or an observation more extreme. Well, in this case, you can't get a more extreme observation because they match up exactly. If my criterion for a good party is how many spare boys or how many spare girls, well, I've got 0 here because I've done a perfect job. So I cut this data set is as extreme as it can be if your measure is how many of one gender or another are left over. Do you see what I'm saying? So we can work out the probability of this now, and that gives me the p-value. Because I know what my null hypothesis is, it says here. So what's the probability? So what's my alpha, which is the probability of, which is my p-value, I guess, which is 1 over root pi times 50. We can just work out that dead easily here. .07, which exceeds the 5% cutoff. So I've got no evidence to reject my null hypothesis. No evidence. Is this wobbling about? No evidence to reject the null hypothesis. Because if the null is true, and you invite 100 children, 7% of the time, you will have an exact match between the boys and the girls. So the null hypothesis is not inconsistent with our data set. Let's try something else. Let's try n equals 1,000. So 2n equals 2,000. Now what's the probability of an exact match? Well, it's going to be 1 over pi, square root of pi times 1,000 equals what? Very much smaller, 0.0178. So that's below your 5% threshold. And if you were to have a party with 2,000 children, of which there were exactly,
The Stirling approximation, does it always slightly estimate above?
I'll come to that. The question was, does it always, it always underestimates. Yeah, I think it always overestimates. Well, we can have a look. We can now assess. Now that I've established how useful it is, and we'll use Stirling's approximation again and again and again. We will have a look at this. Let's go back to my formula here. I'm going to introduce some new notation here. What I'm doing here, I'm rewriting n becomes 9 and then evaluating it. N becomes 2 and then evaluate it. I can do something a little bit more easily. Let me just type it out. You read this, f becomes a function of n, which returns the thing in the curly braces, square root of 2 pi n e to the minus n to the power n. So now, f, it's not a number. Before n was a number, but here f is a function, which is a function of n which returns, effectively, Stirling's approximation. I'll just show you that again. Even now, when I type r, I say f becomes a function of n which returns the thing in the curly braces, which is the square root of 2 blah, 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 blah. So even now I say it to myself under my breath. So now I can just go f of, let's say, 7 to work out 7 factorial. And of course I can get the exact answer, factorial 7. There it is. So the real answer is 5040, and Stirling's approximation gives answer. You see, it always underestimates. Well, I'll show you a correction to it a bit later. Okay, so how about this? You see, it's quite accurate for large n, and it gets more accurate as n gets larger. But even for 1, we know that 1 factorial is 1, yeah? Stirling's approximation comes out with, no, that's not bad, is it? That is not a bad answer. So I can plot the ratio of those two things. I can go plot, oh dear. What have I got here? I've got factorial 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Just as a matter of checking, that number's the same as that one. Of course it is, because that's 9 factorial times 10 is 10 factorial. So I've just added a 0, yeah? So I can plot those. And of course all the numbers are quite small apart from the last one, which is 10 times as big as the one before. But what I can do is plot factorial that over Stirling 1 to 10. Oh, because I called it f. I can call my function anything. So Stirling becomes a function of n. So now I can type Stirling of, let's say, 5, and we've done that before. So now this will work. Now if I say plot factorial 10, now I'm plotting the ratio, which should of course be equal to 1. And it ain't doing too badly. That's factorial 1, which was 8%. Which way around have I got it? I've got the factorial over the Stirling's approximation. Maybe I should have done it the other way around. So see now it's saying it's 92%. So Stirling of 1 was 0.92, wasn't it? So now we're approaching 1 from above, from below, I'm sorry. But even so, we can see this nice regular progression of points showing that Stirling's approximation in terms of the ratio is getting better and better and better for larger and larger n. All right. I'm going to talk about a slight improvement to Stirling's approximation. For most purposes, Stirling's approximation is perfectly good. But you can see it does, in fact, underpredict, and sometimes that's important. So I'm going to talk about a correction to Stirling's approximation, which is Stirling's series. N factorial is approximately equal to root 2 pi n, e to the minus n, n to the power n, times 1 plus 1 over.
I'm sorry, what is E again?
E is 2.718, base of natural logs. Yeah, it's just a number that occurs in mathematics. It's like pi, it just crops up in mathematics. So you can see, as we've pointed out here, Stirling's approximation underpredicts, and so I'm adding stuff onto it. Not very much. You can see the correction's quite small, because for a start it's got a 12 in it, and for a second it's 1 over 12 times n. So even if n is something like 10, we've still got 1 plus 1 over 120. This is a small correction. Let's see how that performs. Stirling 2. Is that right?
You have to bracket the...
I have to bracket it. I got myself, last year I typed that, and it's wrong, of course. and I just couldn't figure out what has gone wrong. But as you point out, what you've got to do is to bracket it there. Oops. Is to bracket it there. What does this one do? This one does 1 plus 1 divided by 12 times n. So this one that I typed first would type this, 1 plus n over 12, which is not what I want. The n's got to be on the bottom. You see how it just... I always put brackets in. I've still not got it right. I've still not got it right. There you go. Okay. So this one here is the first. I think that's right now, is it?
No, that's not. I think it's before the 1.
Put one more after plus one. I mean, after one plus.
What's that?
One plus and then brackets, and then put one more brackets.
That's still, yeah.
That's right, isn't it? Open bracket there. With that's bracketed. Yeah.
Now it's doing 1 plus 1.
That's what I want, isn't it? That's what I want. 1 plus 1 over 12n. That's what I want. That's right, because it's 1 divided by something. What's the something? It's 12n. That's right, so it's 1 plus 1 over 12n.
So they're going to give you n to the power of n times 1 plus 1 over 12.
It would do if you multiplied it all out, but you've got the 1 here as well, so it's not straightforward. Let's have a look at it anyway. Let's try 5. Look how close it is. Even for n as small as 5, look how close it is. It's unbelievably good. It's far, far, far better than you've got any reason to expect it to behave. When you look at the proof of it, the proof is all as n approaches infinity and large values of n. Yes?
Can you just do the regular Stirling algebra?
So it's almost 2 units short. So it's about 2% low, whereas this is 0.02%. It's pretty good. What about Stirling of 1? We know the answer is 1. What about the second series? Even for the smallest value that makes sense in this context, we've still got, it's only 0.1%, slightly more than 0.1% under predicting. So I can show you the ratio as a function of, where's my plot? Let's try this one. And now we can see the ratio between the approximation and the true value. Look, 0.9998, and that's 0.9999. It's approaching 1 very, very rapidly. At some expense, this one's a lot harder to work with, and if I were to show you this binomial probability of pairing using this formula here, then it wouldn't be as easy to do because I've got this bracket here. I'll just give you the next one in the series, and then I'll talk about something else. Go to Google, Stirling's approximation. Wikipedia, excellent source of information for these things. He's written it, or they've written it, in slightly different form. N factorial root 2 pi n. Here we've got n to the power n, and here we've got e to the minus n. He's just written it as n over e to the power n. There should be a series somewhere, just a minute. Don't worry about not understanding all of this. Nobody understands all of it. Oh, and there's the next one, 1 over 12n, which is the next term in the series. And the next one's 288, but I'm not sure if it... Oh, here it is. You can see how, as you get successive approximations, I've got to be a little bit careful because it's only an asymptotic series. It's not convergent. But you can make it, up to a point, more accurate by adding more and more terms here. And so we can put this plus 288n squared to make it even more accurate. But you can see how that's a tiny, tiny, tiny correction. Even with that, we were so close. We were within a hair's breadth That just makes it even more accurate. And you can see that the successive approximations are even more complex. Look at this, 571 over 24. There. If you need it that accurately, I suggest you work out the factorial function directly. Even so, this is a very useful approximation. Right, Stirling's approximation. I'm going to stop there and we'll have a break for about 15 minutes. I need to do one or two things. After the break, I'm going to go back to the Gaussian distribution, and I'm also going to talk about the assignment, which is not due on the 8th. I'll talk about that after the break. Okay, stop there for 15 minutes.